Alrighty. Well, welcome back from break. Hopefully everything went well. Midterm was easy. Meant to be pretty easy. Okay, that's all right. It's a special use case for recursion. So, um, making you use recursion instead of a loop is just a bit of a thought exercise. Is all. Actually, doing interesting recursive stuff takes a little bit longer than I wanted to do on a midterm. So, all right, we're moving into our second half of the course here. We're not going to go as deep into some of these data structures. So we're going to kind of intro these topics. We'll look at them briefly here. And then this is something you'll come back to in your data structures and algorithms analysis class. You'll take deep dives on how these work a little bit better. So we're going to talk about generic trees and priority queues this week. The next week, we'll build our own dictionaries. Those are our maps here using hash tables. And then skip lists, we mentioned it's there. They're sure they exist. And then we'll come back to search trees, a specific kind of binary tree, and then a little bit more in sorting and selection. We did a little bit briefly last time. We'll get a little bit further in here. Again, not all the way into sorting and selection as we go. Um, and then we wrap up with a little seminar on ethics. I actually do have a PowerPoint presentation for that. As much as I hate PowerPoint, it's fine. I can't write code to demonstrate ethics very well, so we'll do that. We've got one last project we're going to pick up before we get to the final project, so we can start that one. Excuse me. Is that rain? Oh man. All right. And then the last couple sessions here, we've got final project work time. The goal is you can get your final project done by the 21st. And great. That way you can focus on your other final exams. If not, don't sweat it. It's okay. You've got the time if you need it. But ideally, you'll get it done early. And these last couple weeks, we'll have a little bit of time as well. We won't have the full sessions, but probably a good, half an hour of each of these. You can work on the final project as well. And this one is done. Where did it go here? We're doing this one in pairs, right? Where's my? Yeah, it's part of a team. So the final project must be a team project. Pairs is about as far as we need to get here. There's not really enough work for three people, but we're going to do this one in pairs. You're going to be a team member for this one. So don't take excuses from your partners. Everybody should be free this time, Tuesday and Thursday, right? And we've got some class time to work on it here to get that one across the finish line. So if we have an odd number, thought we had 10. I got to look again here and see. Um, we might be able to do one group of three, but assume everyone's pairs until I go and count and see who's actually active here. We'll see who all took the midterm. Uh, Usually that'll tell me who's still here or not. All right, that's a more than a pair, I think. Um, that would solve my problem of needing three people. Sure. Uh,
Training LLMs. LLM all over my office. Is there enough training data on it where you can train an LLM to be you?
Oh, I'm sure. I'm sure. Just to feed it my YouTube videos, right?
Yeah.
um, yeah, you can write garbage code too. Don't worry. Uh, yeah, I think it should work out. So we'll aim to get that one going. So we got 2 weeks for this project. So we should be able to start about the 22nd or so for the final project to give you a good month plus that extra week if you need it for finals week. Is it? Am I off a day? Oh, yeah, I'm off a day. Wow. Yeah, that should be 24. 7 plus 7. Yeah. All right. I'll fix that one. Yeah. All right. Sweet. So let's jump into some trees here. Let me fire up PyCharm. So a tree structure is wildly different than anything we've done so far, which is really cool. Trees are an interesting way of storing certain kinds of data, right? If it fits this given structure here, and it's much more of a hierarchical level here. So if you all remember back to biology, no, okay. Uh, we have this way of classifying creatures. Right? You have your kingdom, your phylum, your class, your order, your family, your genus, and your species. I have no idea why that's still in my head, but that's been in my head ever since high school biology here. Um, and everything that's below, right, is part of that top classification. So we get more specific as we go. It's this hierarchical nature. Trees let us store data in some sort of hierarchy, right, where we have these levels of the tree as we go. They don't necessarily have to be um, strictly hierarchical like that. Like inheritance is hierarchical, right? You are a type of your parent class, and that is a type of the parent class as far as you want to go. Same sort of idea here. We could store that in some sort of tree structure if we wanted. What week is this? This is week 9. 9 for trees. So a couple things. I'm just going to draw a picture first here because it's probably a little easier. Oh, I should bring my little tablet, my stylus thing for drawing. So top of the tree here, we call this the root of the tree. Right? So this is our root. I am root, not Groot here. It's the root. Um, and then a tree structure is recursively defined so that each child of this tree is another tree. So each one of these then is a tree rooted here. It just happens to have a parent or a whatever above it here as you go. And each one of these can have some n number of children here. It's going to have n number of children here, right? Each one of those is another tree, right? So eventually you work your way down here where you find a node that has no children. So eventually we get down to where there's a node with no children. We call that one a leaf. So if you have no children, you're a leaf. Yeah, that turned out pretty good, right? No children for a leaf here. And then what we talk about with trees is trees have levels, right? Or trees have a height. So at level 0 here, right, we're at the top. So this is level 0. All of level 0's children are at level 1. All of the level 1's children are at level 2, and on and on and on. So you would say the tree is the maximum, the height of the tree is the maximum level, right? So this tree is a height of 2 here, right? Each individual node, you can also count your level, or you might call it your depth. How deep are you in the tree here? We got lots of terminology. It's a little bit funky. It's okay. So each node has a depth of where it is in the tree, right? So it knows how many parents it has to go up until it hits the top, right? But each of these, right, is another tree rooted in wherever it is, and they don't have to be even here, right? It's just I was drawing it even. Scroll down a little bit. Your trees can be as funny looking as you want here, right? No rules necessarily here. This is just some n tree. So we got a bunch of children here. That's level 2. This is level 3, 4, 5, and 6. Right. So the height of this tree would be 6 here, and whatever we want, you would store in these nodes. Any piece of data, any piece of information here, we could store as we go. This gives us a way to store things in a very different hierarchical structure, like our file system, right? You've got the root is your drive, and within that you've got folders. Within that you've got folders, and your leaf then is a file, right? If you're not a folder, you're a file. You're the leaf. You don't have anything inside of it. Although there's other weird things you can do. That's okay. We'll just pretend. Right. So one way of us storing this sort of information here. So for us to write a tree class, then we can write our class for. This is an n tree here. And then it's a init here. So n tree, it probably needs to know what data it's storing here. And it probably needs to know its parent, which we're going to assume is none until we know otherwise here. And when we're going to have some children, we'll assume is none until you tell me otherwise. Right? So my self.data is the data. My self.parent is the parent. And my self.children. Now, if it's none, I want it to be a new list here. So a none parent's okay. But if I don't have any children, I want to leave it as none. I want to make it like an empty list. It's probably a little easier for me to work with. But again, you can't put an empty list here because then they're all going to share that same list object. It gets kind of messy here. So we can say if children, self.children equals the children, and otherwise my self.children equals a new list. Right? And we got place to store all those children here. And then we can get out our data, we can get out our parent. Now, if we want to be able to add children as we go here, we can have a little function for add child. Now, this would take another entry that we're adding here, or we could just take the piece of data and make it another tree, right? Either way, we want to work with that as we go. Maybe we'll just take the data here. So we'll say the data, and we say self.children.append another entry given that data, and then the parent then is going to be itself. Right? I'm the parent of my new child here. It doesn't have any children, no grandchildren immediately here. So we can add new pieces of data here at any point, go and grab them. Now, again, we're not doing anything smart and protecting. We're making everything public at the moment just to make life a little bit easier. You don't need to go out and get given children or iterate over the children. We'll just give you access just for the sake of illustrations here. We're not building out a nice tree that everyone in the world is going to use ever. We're just showing us what we can build here, right? So that's about all we need, actually. We make children, we can walk those relationships back up here. So for any given entry, I can see how many times it takes, how many parents I have, right, to see the depth of my given tree here if we want, right? And we could print them out. We could print out a level. We could print out all the children. There's a couple of different ways of going about printing all of these things here. So we start to get some fun terms for our algorithms with this here. So if you wanted to print everything, you can print a breadth first traversal where we're going every level. I want to print the first level, and I'm going to grab all the children, print all of them, and then go and get all of their children and print all of them, and then go and get all of their children, print all of them, go and get all their, like level by level by level. We'll go wide first. Or we could go a depth first traversal. We could say, okay, just go all the way down until you run out of children here and print that one, and then come back and then take care of the siblings. It doesn't work quite as nicely with this sort of tree structure with the end trees. We'll look at some other ones when we get to other tree structures here. Um, and then if you wanted to see the height of a given tree, right? Well, that's the max of the depth of a tree, right? So if we wanted, we can add in a function to like calculate our depth here. So we could say, hey, what is the depth of this tree here, right? And then well, that's just one, or if we have a parent, one plus the parents, one plus the parents, one plus the parents, one plus the parents, one here, right? So we can say our level 0 and our current tree is self, and while current tree dot parent, no, current tree dot parent. Okay, well, as long as we have a parent here, right, we exist here, we're going to take our level +1, and we'll take our current tree, and we'll assign it to the current tree's parent. The same idea like we walked our linked list, we're just walking those links here as we go. Okay, go up one, and go up one, and go up one, and go up one, and go up one. Eventually we get to the top where there is no more parent, and we stop counting. Okay? And when we're done, we can return the level. Right? That's the depth of any given tree node. Right? And that should work for any one of these here. Right? At 0, they have no parent, we return 0. At 1, we have one parent. So we're going to go up 1, add 1, and it has no more parents, we return a 1. Sorry, sugar's high. Let's see. Let's take a little more. All right. So from a given node, it's easy enough to see the depth. Now, how do we find the height of a tree? Well, the height of the tree, we have to go as deep as we can here and figure out the max of that, right? So is this path the deepest path, or is this path the deepest path, or is this path the deepest path, or is this path the deepest? That one's a little bit hard to do, right? So there's a couple ways we can go and calculate that here. Like the dumb way is we're just going to go ask every single node for its depth and find the max one of those. Right? Very inefficient because we have to look at every single node and have it count up. So we're going to do a lot of extra work that way. That's okay. It's not the end of the world, but we will admit this one is going to be an inefficient one here. Now, for depth here, it's possible that our tree structure, sorry, this one here, looks like this, and we just have one big chain here. Technically a tree, but it's essentially a linked list, right? If we only ever have one child and 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 one child, sure, we're a tree, but we're just a linked list. So how long is that going to take? Well, it's going to take n operations because I have to get up all possible. And so when we look at worst case performance, it could be O of n, right? There's no guarantee that I'm not in a bad structure here. So it could be O of n for my worst case. On average, it's probably not O of n, right? Is it half of n? Right? Well, even if it's half, we throw away our coefficients, it'd still be O of n. right? Is it a third of n, a tenth of n? It's hard to know because we don't enforce any sort of structure here, so we can't really give you a good measure of this one here other than O of n here. It's not great. You know, even the best case scenario, if we have one parent and it's got like a million children, sure, all those million just have to count one. That's easy enough here. But how often are we going to be in that sort of structure? Again, best case is not all that great here. So if we want to determine the height of a given tree here, again, we're going to go find the depth of every single node here and find the max of it. So we're going to return the max of we want the uh, node dot depth for node in. Oh no, that's not even going to be recursive. Shoot. So we need to go through, get all of them first. So we have to traverse this tree to get all of our children and get all the children's children's and all the children's here into that list and then get the max of that one here. So I have a list of nodes then. We'll start here. Um, and then I need to go and get every single node. So myself is one node here, and then all of my children, and then all their children, and then I'll just recurse as long as we have children here. Um, we need to go add them in. So we want to say for child in self.children, we're going to also calculate the same thing here where they're taking their children. So I need a recursive function, sorry. We need to also calculate is it their height? Let's see. Um, sorry, I can go look at the book here. He's got a solution. I was trying to do it without looking at it here. That's a bummer. All right, so let's define a little traversal. This is our breadth first traversal. Traversal. There we go. Got an extra S in here. So if we're going to traverse here, we're going to give you every one of our children, and then we're going to recurse on every one of our children's doing a breadth first traversal as well. So we're going to get some list of nodes here, and then we're going to have to pass in the nodes as we go so we can start adding to that list here. So my nodes can equal none to start. So if nodes, or if not nodes, if it doesn't exist, starts off as a brand new list here. Otherwise, we can go and add to it as we go here. So we're going to add, I'm going to take my nodes.append self.children, and then for child in self.children, let's recurse on the breadth first traversal, self.breadth first traversal. I'm sorry, the child breadth first traversal given the list of nodes here. And it can recurse and give all of its children nodes into the list. And it will recurse to give all of its children's nodes into the list, give all of its children's nodes into the list here. So eventually we'll run out of children to add to the list here. When we're done, we can return our nodes list here. That should give us all of those here, I think. Was it not? Oh yeah, it's protected. That's okay. We'll go through and call it the same thing. So we'll get our list of nodes then is self dot breadth first traversal. And then for, I guess we just need the max of node dot the depth, right? Node dot depth for node in nodes. We'll calculate the depth of each of those and figure out which one is the max. A little bit convoluted here, but I think that ought to take care of it for us. Let's see if it works. So we can make an entry. Tree is an entry. Given, I don't know, some data. The data doesn't really matter too much here. So then tree.add child, we'll add a 20. Tree.add child, we'll add a 30. And then my child will be tree.children 0. And then child.add tree, add child, we'll add a 40. Child.add child, a 50. And then child.children, of 0 again here, and then we'll add one more. Add child 60. And then we want to print our, so it should be the height of the tree, right? Should work off of any one of these should calculate the same height, right? So let's do our tree.height. Let's put a breakpoint in and see what happens, right? We'll run in the debug mode and see if we get our tree structure, right? So we get our tree, right? Its state is 10, it has children. It has another tree and another tree, right? This tree is a 20, this tree is a 30, right? We added the 20 and the 30. This 30 has no children, this 20 has children, right? Because we added children here. So we added more trees here. We added a 40 and a 50, right? And then this one here, the 40, has children, right? That one has a child of 60. That one has no children. So levels then, right? It's level 0, height of 0 at this one here, height of 1 with these ones, height of 2, height should be 3, right? Should have 3 levels plus the root here. So we go and recurse then. Let's step into our function here. We get our nodes, then we're going to do our breadth first traversal and check and see, okay, we have no nodes to start, so we get an empty list. We're going to go add all of our children to our list here. So we should add the 2 children. And then for every child in our children, let's go recurse and add those to our list here. So that's our list of nodes here. So our list of nodes. Let's see, we got our tree. Oh, it added, shoot, I didn't, append is the wrong function here, sorry. We want to extend, because extend should take another list and add each individual item here, right? Rather than, it gave me a list of lists, and I want a list of lists here. So let's try that one more time. All right, so we'll step into this one here, and then we'll step into our traversal. Put it on nodes. Okay, now individual nodes look good so far, and then we're going to go traverse into this one here. We did pass it nodes, so then this self children here at this point, right? This was the 20, and it had children of the 40 and the 50, right? So we go and extend those into the list here. Now my list has the 40 and the 50, right, as we go. And then it's going to go through its children here, and it's going to check and see, do we have children here? Yes, we have one child. So it's going to add that one to our nodes list. So then nodes now has the 50 or the 60, right? And then it has no children, so it should be done with that one here. Shouldn't add anything else. Yeah, now we should be done here with our children. Return the nodes, return the nodes, return the nodes. Right, it's kind of unwinding its recursion here. Return the nodes. Right, so now we have our list of nodes, right, with the 20, the 30, the 40, the 50, and the 60. Now for each one of those, we're going to calculate the depth. Each one of those nodes will now count how many parents, how many generations it has, right? How many levels above it has here. And eventually one of them should get us the max height, right? The max of that would be 3. You all look very excited here. And you can imagine this one now is painfully slow here because not only do we touch n nodes here with our traversal, but all those n nodes have to count up, going up to the max as we go, right? So not ideal here for our calculation of performance. This is, of something probably pretty terrible, right? Because we've touched every n, and in the worst case, that n then has to count n items again here. So I think that gives us to n squared, right? If it's n nodes, and then that n node has to touch n nodes for every n node, right? Uh, not great here. That's okay. There's a couple things we can do to optimize here. That'd be nice, right? Instead of counting every single one, we want to essentially work our way down as we go, and we can throw out anything that is less than the furthest that we've gone, right? Like when we looked at the maze solver, we said, hey, I know my shortest path was 12 here. If I've gone more than 12 steps, just stop. You're not going to find a shorter solution that direction here, right? So a couple ways we can optimize. Again, this is for this N tree structure. It's interesting here. You can finish out in the text if you're interested. Again, you'll hit this sort of generic N tree next time. But they exist. They're not very performant, even if we add in some cool bells and whistles. But that's just the nature of it because it can have n levels or n children at every node. Who knows? Right? There's not a good way to control it here. So if we look at a different form of trees here, let me go add. I should call this one something different here. This will be our n tree. Let me rename n tree. Let's go add another class here. Let's call this our binary tree. So a binary tree, instead of having n children, has two. It has a left and a right, and that's it. It's all we have. So we know then at most we'll have two children. Maybe we'll have one. Maybe we'll have none. Right? The textbook takes you through this fun process using inheritance, where he defines a base class and then extends all the classes into specific ones. I find that more confusing, but it's fun to see it both ways. So I'm just going to write it straight here. If you want to see his version with all the inheritance, it's cool because it has done some of the work before. You don't need to redo some of that work. It's okay, right? Like we could technically still calculate depth the exact same way, but that's okay. So we'll write our binary tree, define our binary tree. Um, so now given some data, sure, so self.data is the data. And then we might have a parent, right? So parent is none, parent equals none, and then we might have a left child and a right child. I'm going to assume they're none until you tell me otherwise. But no more dealing with lists here as we go. So self.parent is parent, self.left child is the left child, and self.right child is the right child. Right? So we can set any of these here, right? If you have one, we shouldn't be able to go change it. Right? It'll mess things up here. And you can't just add any number of children here. You can just add a left or add a right. So we can say, let's add left given some data. And if my left child, or self dot left child is not none, we'll raise I don't know, some sort of value error and just crash here. I already had a child. You can't replace it here. Otherwise, then we can go and say my left child then is a binary tree given the data. Self is the parent. Right? Cool. And we can do the same thing for add right. So add right. And we just care about checking if we have a right child. And then setting, oops, that was the wrong word to replace. Let's replace left with right. Okay, we're still the parent. Okay, that works out. So other things we can do then, if we have a given node, we can see what's my sibling node. Maybe, right? I might have a sibling node here. So we can say get sibling given a node. So if we have a parent, we go to that parent and see, do we have the left or the right? Okay. If we don't have a parent, it's none. So if self.parent is none, return none. Right? Otherwise, then my parent then is my self.parent. Now, this just saves me a little bit of typing here. You don't have to save it out here. I don't know. I like not having to type it a bunch of times. So now we need to see, am I the parent's left child or right child? Because I don't know which child I am of my parent. I just know who my parent is. Right? So you need to see if parent dot left child is self, then I return parent dot right child. Right? If I'm my parent's left child, you must want the right. You want my sibling. If I didn't return the right, I'm going to return the left, because I must be the other one. And these could be none. They might not have one assigned. That's okay, right? You might get a none back if we don't have a parent. You might get a none back if you don't have any of these here, right? But now I can figure out what is my sibling here, right? No matter what node I am, going this way. And again, the height works the same way. We'll just steal that one as we go. Or sorry, depth here. We'll see what level I am, right? We'll just keep going up to parent, going up to parent, going up to parent, going up to parent. The same thing for depth here as we go. All right, and then if we wanted the height of a tree, there's an easier way we can do height. I'll grab that one in just a minute here. But if we wanted to traverse this tree here. Again, we did the breadth first traversal. We went through every child. We could do the same idea, but now this one is a little bit easier for us to do the depth first. We can go as far down as we want, and then we can come back up and check the other ones here. Um, so for our depth first, um, you do your left, yourself, and then your right. So every time we process a node, we see, can I go to the left? If I have a left, okay, we'll go left. And then repeat. Does that one have a left? Repeat. Does that one have a left? Repeat. Does that one have a left? Repeat. Does that one have a right? Eventually we'll run out of left children here, and then we can process ourself here, and then we go to the right. I'm sorry, we want left and then right and then self here. Uh, right. Check the left children's, check the right children, and then eventually we'll come back and do myself at this level here. So we're going to go as far down as we can with our children first. Right. So let's make a binary tree here. So we'll do our tree as a binary tree. I'm given 20 again. Tree dot left child, then we'll give a 30. Tree dot right child, we'll give a 40. And then left was my tree dot left child, and left dot, um, yeah, oh no, it's add left and add right. Shoot, add left and add right. There we go. Add left here, let's give like a 10. And then a left dot add right, we'll give 25. And then let's just do the left again here. Will be the left dot left child. And then left dot add right. Let's add, I don't know, a 1. Okay. So we got a 20, and then it has 30 and 40. Should we draw it out? Should we draw it?
Yes.
All right, I like drawing. Drawing's fun. We go down to another page. So the first one, we put 20, right? And we said, okay, let's add a 30 to the left. So we have a 30 and a 40. That's a 40 there. To the left of that, then, we added a 10 and a 25. So we added a 10, and we added a 25. It's harder to do with a mouse than it sounds, I promise. I'll bring it on Thursday. And then to the left of that left, we added a 1. We added just a 1, right? So here's our tree that we've created here. So to go depth first, we're going to start here and say, okay, do you have any children? Do the children first. If you have any children, do the children first. If you have any children, do the children first. So eventually we'll get down to the 1. It doesn't have any children, so we'll process the 1. And we'll come back here. We're at the 10. Does this one have any children? No? Or we did the left already. Has no more right children, so now we can do the 10 here. The 30, right, was processing the left. We finished that here. It's going now over to the right child. Now we'll get the 25. And okay, we got that one. Then we come back, we did the 30 here. And then we did the left child of 20. Now we go to the right child. That one's 40. We did all the children here of 20, and then we get out to 20. And it doesn't really make a lot of sense here, but we went as far deep as we could first, going on the children with this traversal. So our traversal for this one here, we'll say print depth first, depth first. So to do this one, we're just going to recurse on our left child, recurse on the right child, and then print ourselves. Right? So we're going to call self dot left child dot print depth first, and then self dot right child dot print depth first, and then we'll print self dot data. Right? Go to the left, go to the right, print my data. And because this is recursive, we'll go all the way left, 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 left. We should get out. Oops, no, add right. Did I mean add right? Did I spell? Oh my goodness. Add right, add right. This one here, R-I-G-H-T. I didn't even get it because it doesn't know that it was a tree. It couldn't determine that the left of the left was also a tree. I didn't add the strong type hints here. All right. Oh, it didn't print anything. It should have at least printed, right? Oh, I never called it. Tree dot print depth first. There we go. Now if we call our function, uh-oh, non-object has no attribute, print depth first. Well, if my left child is none, you can't print here. So if self.leftChild, right, then do it here, right? It's if it's not none, essentially is what it's what's saying here, right? This if, then if self.rightChild, we'll do the right child, then we can print our data. There we go. And we get out our 1, 10, 25, 30, 40, 20. I think that's what we said here. 1, 10, 25, 30, 40, 20. Cool. So we did our depth first traversal here. The other one we can do is we can do what's known as an in-order traversal here. They print in order traversal. Now this one is where I was going. It's a left, center, right. So we go to the left recursively. When we run out of lefts, we grab ourselves, and then we go to the right. Not super useful with just a generic binary tree. Once in 2 more weeks, when we get to binary search trees, this will make a whole lot more sense. It's okay. It's not the end of the world. So we essentially just do this exact same thing here. We just swap the order around. So go left, self, and then right for this one here. So if you want to print in order traversal. Now we're going to get all the way left first. So 10, I'm sorry, 1, 10, and then we get the 30 instead of the 25 here, and then the 20 instead of the 40. They should swap. Right? So then the right child is the last thing that we did here. Right? And not the most useful thing at the moment here, but that's okay. We're getting there. So this is the binary tree structure. Now, a couple things about binary trees here is that storing them with these links works, right? You just have to traverse your links here, but there's another way we can store them here. Somebody really smart figured out, well, really, it's if we only have 2 children and then 2 children and 2 children, right? At this level, I have 1 item. At this level, I have at most 2 items. At this level, I have at most 4 items. At this level, I have at most 8 items, and then 16 items and 32. Does that look like anything familiar? Our powers of 2? Yeah. So if that's all that is here, I can store them in a list and use indexes to know how to traverse. Believe it or not, it works. So this then would be index 0. This would be index 1, index 2, index 3, index 4. If we had children, it'd be index 5 and 6, index 7, 8, 9, 10, 11, 12, 13, 14.
It's always left to right.
Yeah. Yep. Yeah. So it relies on us forming them in this given structure here. So when we think about binary trees here, you can be a complete binary tree if every level is full. More fun terminology here. So this form here, we're not complete here because we've got levels that aren't full, right? So if we wanted levels that were full, right, we'd have some value here. This one would have 2 children here, and this one would have 2 children, and this one would have 2 children, right? They'd be complete. Okay. You could also be a full binary tree if you're complete at every level except the last level, and then the last level, everything is as far left as possible. So if you've got children over here, you're full because the top part of your tree is complete, and then the last level has everything far left. And we can add another node here, add another node here, add another node here, node here, node here, node here, node here. We would fall into that complete form. What's nice about the complete form is it fits in a list with no extra space, right? This one that starts to have gaps here, we've got extra space in our list. Not great, not the end of the world, but we're going to have some openings here. So if we force our tree into this complete structure, we know the next place it goes is just the next available index here. We can start to build out a fun structure called a heap here. And heaps are lots of fun. So let me add a new Python file here for a heap. Our class for heap then. Define our init here. Now we probably don't need any data yet here, and we're just going to give them a function to add something in here. So we'll have self.data is a list. Right? And every time you want to add something, we just go add it, we append it to our list. Right? So then we can define an add data, or we'll just call it append, right? I guess. Excuse me. given some data, then goes to the end of our list, data.append, the data, sure, we have added it in here. Now, it's not really great and doesn't really look like a tree because you can't really add to the left and add to the right here without doing some fancy arithmetic. But turns out you can do some fancy arithmetic. So for any given node here, if I know what its index is, I can find its parent and I can find its children. If you tell me the index, which is pretty cool. So for this index here, right, drawing it out as like a table usually works out pretty well here. So we're going to draw, this will be our left child, this will be our right child, and then we need a parent here, and then yourself here. So if your index is 0, you have no parent, right? We're at the top, there is no parent. Your left child index is 1, your right child index is 2, right? If you're a 1 or a 2, your parent is 0, right? So this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Right. So for 0, or for 1 and 2, parent is 0 here. The left child of 1 is 3. The right child of 1 is 4. So we get 3 and 4. For 2, the left child is 5, and the right child is 6. So we get 5 and 6 here. Right. So there's starting to be a little bit of a pattern here, but let's do the next level. So for 3, 4, 5, and 6 here, the parent is all, I'm sorry, for 3 and 4, the parent is 1. For 5 and 6, the parent is 2. Right? For 3, your left is 7 and 8. So for 3, we 7 and 8. For 4, your parent or your child is 9 and 10. 9 and 10. And then for 5, your children are 11 and 12. And for 6, your children are 13 and 14. I've done it before. I know the arithmetic. It's okay. It's not super magic here, but you're doubling yourself and adding 1 or 2. Right? So 1 doubled plus 1 plus 2. 2 doubled plus 1 plus 2. 3 doubled plus 1 plus 2. 4 doubled plus 1 plus 2. Right? Because we're doubling, right? We know it's that powers of 2 pattern, and then you just add 1 and 2. To find your parent here, it is half of yourself, or I'm sorry, yourself minus 1 halved. So 1 and 2 minus 1 halved down to 0, right? Floor division. 3 and 4 minus 1 gives us 2 and 3, floor division 1. 5 and 6 minus 1, floor divided by 2 gives us 2. Right? We're going up the level, right? We're reversing the plus 1 plus 2 process with the floor division. So if I want any given parent of a node here, right? I know the index is at minus 1 floor divided by 2. Right? So for any given node that I'm at, I can quickly count and see where is it. Or if you want the left child or the right child. So if we don't want just regular appending here, if we want to be able to add them in, right, we can go do our calculations. Now, just adding to the end doesn't really do us a lot of good here because we're just sort of jumbling everything up into this sort of structure. We're fitting it into a tree structure. It doesn't really make a lot of sense. So just a basic heap is not all that much fun here. What we can do is we can use that sort of heap structure to build what we're going to call a priority queue. Priority queues are one of my favorites here. Now, sort of like the fast pass lane here. If you paid a lot of extra money here, you go to the front of the line, you get picked first. Right? Everyone else, you just get thrown in the line. It's a regular line, you'll get picked eventually here. A much more classic example of priority queue is the emergency room. Right? They don't take you in, first served, first come, first served. Right? They take you in order of your severity. Someone who's having a heart attack should probably go in before the person who's vomiting. Right? That sort of thing. Someone in a car accident is going to get in first before you who have a bad cold. Those sorts of things here. So we want the priority stuff to bubble up to the top here so we can pick it off here. So with our rule with the priority queue is we want to keep ourselves in that tree structure. We want either you can be a minimum priority queue or a maximum priority queue. Either way you want to define what's the first one we want to pick, either the lowest or the highest. Doesn't matter. I'm going to do a min priority queue. Right now, so we'll have the lowest at the top. So we're going to have that sort of heap structure here as we go. so that the smallest item will be at the top as we go. So we're going to define an init. So we're going to have self.data. We'll make this one private here. We don't want people messing with our data individually here. And then we can go and append something here to the heap here, given some data. Now, what I need to know is what index I'm putting it at, and then how to get it into the right priority. Right? So if it's the smallest item, I want it to go to the top. If it's not the smallest item, it can stay down below. So to make priority queues work here, we keep a cool structure and we keep a very specific rule set. So the rule is you can't be smaller than your parent. Right? So your children must be greater than the parent. Right? So children greater than parent, that totally came out really clean here. So children, no, that's backwards here then, right? If children are greater than the parent, have to be greater than the parent, right? That's the rule. Now, we're going to run into issues here if we don't keep this in somewhat of a more sorted order here, because I might have, say, if my parent is 2, and what if I had like a 7 and a 12, if I wanted to add, say, a 9. Well, if we're keeping that complete tree form, the next place I'm going to put it is over here. It's a 9, right? Is it bigger than its parent? Yes. So we're okay. It can stay. Right, that one's fine. Oh, if I wanted to add a 6. Well, the next place it's going to go here is this node here. It's going to be a 6. Is it greater than the parent? Yes, it is. Well, now I need to swap. So we're going to swap positions. We'll take the 7 out here. We'll take the 6 out, and we'll change them. We'll put the 6 here and the 7 here. And then we have to recurse. Is the 6 now greater than its parent or smaller than its parent? No, it's not, so it can stay. Right? It's okay. And now for a 12, let's add, say, the number 1. So we'll come over here, we'll add a 1 here. It says, are you less than your parent? Yes, then swap. Right, so we're going to swap. So we'll move the 12 down below, we'll move the 1 here, and then we recurse. Oops, sorry, that's just a 1 here. Are you less than your parent? Yes, you are. Okay, so let's swap. So now we swap the 1 with the 2, 1 and the 2, and the 1. So adding's not so bad, right? We bubble them up, or the technical term here is we upheap. It's one of my favorite technical terms. We upheap the value until it gets to the top of the heap here. Now, if you think about if we're keeping ourselves in this complete binary tree form here, in terms of n items here, what's the worst case number of swaps I'm going to have to do? What's less than n, right? It's going to be logarithmic of n because every next level is half. So it's log of n. So because we're only having to do n levels, or like the log of n levels, right? So the height of your tree is log of n if you're in this complete form. Then you only have to do at most the max height here, which is logarithmic. So it performs relatively quickly for keeping it in somewhat of a sorted order. Right? That's pretty nice. Now that's upheaping. Now to remove something, you're going to take the top thing. To get at the top thing, it's right at the top. We can get it right away. Immediately, it's index 0. We have it. Right? Life is good. We can just grip. We're going to take it out here. So, all right, now we're going to serving the next patient in the emergency room. Who's next? Well, that's number 1 here. We take number 1 out. So what we do then is we down heap. So we're going to take the last value here, the 12, we're going to swap that back into place, and then we have to down heap it. So for down heaping, we have to swap with the smallest child here. So 12 doesn't swap with 6 because 2 is the smallest child. So we're going to swap with the 2 here. 12 goes down here. Now we're still in our priority queue form. Every child is greater than its parent here, and the smallest is at the top. Right? And we can add in the next item here. So we're going to down heap values, and we're going to up heap values as we add things here. It's fun. So adding something to our priority queue, then we need to know what index it's going to, right? So the index it's going to is the length of my data here. So the index is the length of self.data, right? Because length will be the next index it gets added as. So then self.data append the data. That's an underscore. That one's private here, right? So now we've put it in at that index, right? If I had 1, 2, 3, 4, 5 things, it's going to become index 5, right? Because I have index 0, 1, 2, 3, 4. Right? We're going to put it in at index 5 here, this way, right? Now, I know what the index is, so I'm going to add some helper functions. Now, no one else needs to use these. These are private functions here. So this is the um, parent index given an index, right? So we're going to return index -1, floor divided by 2. Right? That's the arithmetic we already looked at here, right? And then we can define a left index given an index. We said that was return index times 2 plus 1, right? Doubled and then add 1. Or is that our chart here we made? Totally legible, right? Double, add 1. The right child is double and add 2. The left index, right index, double and add 2. Right, so we can calculate all those indexes that we need to here. Oh yeah, they can be static. So they don't really need the self instance here for us to calculate those things. So it's telling us we can make them static. It's okay. It's not going to hurt anything right now. So appending, we do this. And now we need to upheap, right? So we added something in, now we need to make sure it's in the right spot here. So we're going to call self.upheap, upheap, given the index. So we got to write our little upheap function. Define upheap given an index here. Now, when we get to 0, there is no parent. Our arithmetic will fail because trying to floor divide a negative number, I think we'll still get 0. We'll just end up recursing forever. So it won't mathematically fail, but we just want to stop. So because this is a recursive function, our base case is we got to index 0, right? Can't go any higher, or you don't need to swap. Stop recursing, right? So there's two different base cases, right? So this is a recursive structure, recursive function here, which is fun. So we can say, hey, if my index is 0, right, then we're done, right? Or really, if it's not 0, we can keep on going, right? Either way you want to write that one, that's okay. We'll say if it's 0, we just return.
It's less than or
Well, so we're never going to calculate of 0, right? Because if it becomes the very first item, we're going to get a 0, right? We'll say, hey, the length of data is 0. We're only ever going to call this with a 0 or a plus number. And it should never get called with a negative number. We could put it in just to be safe, but it shouldn't happen. So we bail on that one, right? And then we need to check, am I less than my parent? So if my self.data at the index is less than the self.data at the self.parent index, given the index, there we go. Oh my goodness, right? If it's less than the data at the parent's index, then I need to go do something, right? So what I'm going to do is I'm going to swap. So we'll just change the values around, and then we're going to recurse. So it might be a little bit easier to store some of these things here. So we can say, hey, my parent index. Again, the book likes doing this in 2 lines. I'm not really fond of doing it in 2 lines. I'd rather use a couple more lines to make this look a little easier here. Then so our parent index will equal this here. If it is less than, then we need to go swap. So self.data, self.data at the index. Now, in Python, you can do this cool comma-separated thing here. I don't know if you've seen this very often. We can assign then this one, but swap them. Somehow this works for you. Rather than saying, hey, this one's a temp, right? We can just say, okay, let's take this first thing, this second thing, and assign them the first thing and the second thing. It'll change them both at once. It's essentially like making tuples and unpacking tuples behind the scenes here.
Like leveling one X and Y, and then trying it swap.
Yeah, just swapping here. So if it's less, we swap, right? So we've swapped, and then we need to recurse on self.upheap on the parent index, right? Keep on going. If we're not less than our parent, we're done. Nothing else has to happen, right? The return is sort of implicit at that point here. right? We're just returning nothing. We don't need to do anything here. So I guess it might be easier if we just say if it's not 0, then let's go. If it's not 0, go do some work here. If it's 0, nothing happens, right? Uh, should be okay like that, I think. That makes sense for upheaping. So eventually we'll get it to where it needs to be, and we're done, right? So then that's appending an item, and then we can like get min here. Now we're going to give back that value at index 0. We're going to hang on to it for a second here. So my value is self.data at index 0, right? Well, that's the minimum value here. Now we need to do the swap here. So then we're going to take the thing off the end here, and we're going to put it back in this place. So self.data of 0 then is self.data.pop. Take the last item off, put it in here, right? Now we need to start downheaping. So then self.downheap starting at 0, right? So start moving this one down. So now for downheap, we got to go write that one. Define downheap, given an index. And again, this one is recursive here. We're going to swap with our smallest child, right? So we need to find what the smallest child is, right? And it might be none. We might not have a child, right? We might have one child. We might have two children. So there's a couple cases we have to look at here as we go. But essentially, we get our left child index and our right child index. Let's go check them. So our left child index then is the self.left index of the index, a right child index, self.right index of the index, and we need to find the smaller one if they even exist, right? We could have gotten a none. I'm sorry, we do get values back here, so we need to see if they're within range here. So if my right child index is less than the length of self.data, right? It's a valid index. Otherwise, we're going to crash here. So if I have a right child, what we can do is we can assume that's probably the smallest child until we know otherwise. Okay, so we can say my smallest child index is the right child index. And then we can check if I had a right child index, I have to have a left child index, right? So actually, let's do the left one first. So that's probably a little bit easier. You can say if my left child index is less than the length of self.data, then our smallest child index will be the left. And then if we have a right, then let's go see if it's smaller. So if it's valid, let's see if it's actually smaller. So then if the right self.data at the right child index is less than the self.data at the left child index, then the smallest child index will be the right child index, right? So it's the left if I have a left, and then if there's a right, it's the smaller of the two, right? If I don't have a left, nothing else happened here, right? We never got a smallest child index. So if we have a smallest child index, then now let's see if we're smaller. So if my smallest child index is a value, right? And then self.data at the smallest child index is, so we want to take, if it's smaller than us, so if this one is smaller than the self.data at the index, then we're going to swap. Right? Yeah, might not be referenced before. Okay, so I'm sorry, we got to start it as something here. So we'll start it as none. Goodness. Right. So it starts as none, maybe the left, maybe the right. Right. Then, if it exists and it's smaller, we need to swap. So we'll swap our values here. So we'll take these ones and then we'll assign them, comma, equal that one again here. Swapped around. So swap the two here, and then we recurse. So we call self.downheap on the smallest child index. Right, we found the smallest one. Now keep on swapping. Keep on swapping, keep on swapping, keep on downheaping as we go. Right? Make sure that one isn't less than its, or make sure that one isn't bigger than its children here. We go in the right order here. If the child is less than, yeah, if the child is less than, it needs to be above. It has to be on top, right? At higher level here. So eventually we're done with this one. So again, it will recurse its way through here. Downheap? There's a typo in downheap? Okay, sure. That was a little bit harder than up heap. That's okay, right? Just we have to figure out which one is the smallest child here. We do the swapping. Okay, so to get them in, we go grab it, swap the last one in for the first one, and start down heaping. Eventually, we can return the value here. Whatever happens with down heap happens, and then we can give back the value when we're done. Right? So I can add something, add it to the end and upheap it. To get them in, we grab the value, swap to the last one, start down heaping it. That keeps it in that order here. Right? So that's our min and priority queue. So we should be able to use this one if we want here. So we'll take a priority queue equals a min priority queue. Now we can probably just add a bunch of random numbers here, right? And it should work. I don't know if we need to call them out ourselves. We'll say for number in range, I don't know, what do you want to do, like 50 numbers here? Take our priority queue and we'll append random.randint. You want to do like 1 to 1,000 here? Yeah, we got to import random, please. Import. All right, so 1 to 1,000. Now, duplicates are actually okay here. It's okay to have duplicate values. We're only going to make sure that you're not less than your parent. So if we end up with two different 2s in here, let's see, where was our queue here? If we added another 2, we're going to add it into the end here. So here's a 2. Is it less than its parent? Yes, so swap. So it swaps the 2 in with the 12. Right? And then says, are you less than your parent? No. It's fine. We can have duplicates. It's not the end of the world. It's not going to break anything in this form, which is cool. Right? So we added them all in here. So adding n values, then, each time we add is going to take log n operations. Right? So we're at n log n, add in n values to this thing here. And then while, I guess we should probably have a length of this one, right? So we'll have or it is empty. We can return self.data, or length of self.data equals 0. And we can also define a length, return length of self.data. Tell me how many items you have. So as long as they're not empty, is empty, or not is empty. I'm going to print priority queue.min, get min. So we'll add 50 things, 1 to 1,000, and we'll pull them all off here. Each time we pull something off here, it's logarithmic in n. So it's keeping it in this sorted structure, this sorted form here, semi-sorted, right? And it takes log n operations for it to downheap the value we just swapped. Might go all the way down to the bottom level, might stop somewhere in the middle here, right? We'll give that a run. We should get, we got out here. Oh, we can't swap when we're the last one here. Shoot. Once we pop it off, there is no 0 to put it at. So if it's the last one here, okay, let's see. So before we do that one, I guess, we can't assign. If length of self.data is 1, then I guess we do something special. Otherwise, we do this one here. Right? Otherwise, we just return pop. Right? If we only had one thing to pop it off, there's nothing left here. There's no swapping that has to happen. Right? I guess at that point. That should keep it from crashing, hopefully. There we go. All right, we should have 50 numbers, 1 to 100, in sorted order. Right? And this took us n log n to add them all in, and then n log n to get them all back out again. There's n operations each time log n. So is that 2n log n? Is that how the math works? N log n twice? So we get to throw away our coefficients. So we have essentially sorted some numbers here in n log n operations, which I think is faster than we were able to do with our selection sorts and insertion sorts that were n squared operations, right? So we're faster, which is pretty cool. And we can use this to keep data in some sort of structure here in this heap form where we always have the smallest at the top. Right? So it's a fun way of us storing information that we need to as we go here. That makes a little bit of sense? All right, sweet. Let me go back here to our projects real quick. So we did our stacks and queues. We did checkers. That was our recursion project, right? And we did our classes. So the last one we're going to do is linked objects. So we're still talking about linked objects, not a linked list itself, but objects that just have those links here. So if you give me just a second to shamelessly copy paste here, let me go grab this one here from last winter. Linked objects. Where'd it go? Linked objects. All right, we're going to do a terrible thing here, and it's okay. It'll work. It's just an illustration here. So this is project 3. This is our last individual project here. Linked objects. So 2 weeks for this one here, right? Puts us at the 24th, not the 22nd. Sorry about that. I can figure out what time it is here. 2 o'clock. We'll do 20 points for this one. All right. So not linked lists here, right? Linked objects. So I'll give you the rubric in a little bit here. So we're going to write a class for commander. This is a terrible version. It's okay. We're going to have an attribute for hit points and an attribute for the first creature, or sorry, not null pointer. That should be none. So the bad translation from C++ here. The first creature we have in our control, or none if we don't have a creature. So the commander, or like the how linked list had nodes and nodes were linked here. Commander has a creature, and creature are the links here as we go here, or none if we don't have any. And then we're going to have a creature for add creature. Given a creature, make sure you make a deep copy of it here, not a shallow copy, right? Making sure we're getting all the attributes copied off of it, because this one will reference other creatures that reference other creatures that reference other creatures. So we want to make sure we're getting an actual copy, not that shallow copy. We don't want 2 creatures with the same chain here. And then we want the specific order for our creatures to be stored. So we have the creatures with the highest defense first. If they have the same defense, we have the highest strength, then the next one here. If they're both the same, it doesn't matter. Okay, and then for creature, right, it has a attribute for strength, attribute for defense, and an attribute for the next creature. It's what's the next creature in the chain here. Right, so this is just singly linked here. If you want to add another backwards link, go for it. I'm okay with you adding more here, but at least it's singly linked here as we go. So we're going to add creatures to our collection. Some n number of creatures, doesn't matter. We just keep adding them in the chain as we go here. And then we're going to have a method for battle given another commander. So one commander can battle another commander, right? So what this does is it goes in the list of creatures. The first creature battles the first creature, right? When the creatures fight, their strength is dealt to the other creature, the opponent's creature that we're battling, right? If the damage dealt is more than its defense, it dies and you remove it from the collection. Both creatures can die, one creature can die, or no creatures can die. Right? Different things can happen depending on their strength and defense here. Right? If there's a remaining creature, and all of one commander's creatures are dead, the remaining creature's strength is dealt to the commander. So the commander loses from his 40 hit points here, that creature's strength, the next creature's strength, the next creature's strength, on and on and on and on as we go. If both creatures survive, the fight's done. Right? So if both of ours had like a strength of 1 and a defense of 2, no creatures die, nothing happens. Nobody takes any damage here. Right? So 3 things can happen. The fight stops when both creatures survive, one commander takes damage from the other creatures, or both commanders are left with no creatures. No commanders take any damage, because all the creatures have died. Right? They could kill each other. Right? So that's the battle method here. Right? That creature class here, when a commander has 0 or hit points or less, the game is over. Right? And they just go and battle, and add a creature, battle, add a creature, battle, add a creature, whatever happens to be here, whatever given sequence here for how this works. Right? So you don't need to have a main function here that actually runs anything. You just need the commander class and the creature class here. And battle needs to work, but you probably want to make sure that battle does work. So if you want to write a main where you're testing it yourself, you don't have to do unit tests for this one. We've already done some unit tests here. That's a fine way to do it here. If you just want to do it main, that's okay too. It's not going to hurt anything here. So I want to make sure that the right things happen, right? Because a couple different scenarios can happen here as we go, right? And at some point we just say, hey, the game's over. Again, that's kind of really silly here. I'll just take that out because there is no game we're playing here. But that is what would happen, right? When you run out of hit points, eventually you're done. But you should be okay there. No, we can't control S safe. All right, so we publish this one. I'll add the rubric for you in just a minute. I know you guys got to get going here. And I'll see you on Thursday. All right, sweet. Yeah, we got through a lot today. That was good. We'll take a look at how the book does some of the examples on Thursday. Kind of compare and contrast. I think it'll be fun.